This is motion of a particle in the absence of external forces. So particle is when size and shape do not matter. And kinematics is motion in the absence of forces. The types of kinematics that we learned were rectilinear. This was straight line motion. Curvilinear. The curvilinear is motion that is in 2 dimensions, but there's still no orientation change. So something might move up and down, but its orientation does not change. A subset of curvilinear motion is projectile motion. So that is where an object is flying through space only under the influence of gravity. And then we had relative motion. So relative motion was one thing with respect to another thing. So we had the VA equals VB plus VA with respect to B, that kind of deal. And then we had coupled motion, which was the pulleys. We remember for pulleys, you just count the ropes. Now, formulas for particle kinematics. So we had the fundamental differential equations. For the linear case, we have V equals ds dt, and A equals dB dt equals d squared s dt squared equals V dV ds. So to solve, we just separate and integrate. So you move whatever's in the denominator over to the other side and you do the integration. Then later on, for rigid body kinematics, we covered the angular, which is real similar to this, where we had omega equals d theta dt and alpha equals d omega dt equals d squared theta dt squared equals omega d omega d theta. Then we also had the displacement, which is just the change in position. So that is like delta S equals S final minus S initial. And then we had the averages. So average velocity equals change in position over change in time. And average acceleration equals change in velocity over change in time. So the difference between the average and the instantaneous is that the delta is a lot bigger for the average. Now, speed is a scalar, velocity is a vector. So velocity has a magnitude and a direction. But speed, v equals the norm or absolute value of the velocity vector equals square root of bx squared plus by squared. And if you had more dimensions, you add those on. For curvilinear kinematics, we had vectors. So we had like r for position. For rectilinear kinematics, it's only one dimensional, so it's not a vector, it's a scalar. We used s. Now, we had some special cases. So for projectile motion, we had constant acceleration in the y and constant velocity in the x. So for constant velocity, so s equals vt. We saw this for projectile motion. The parallel is x equals x initial plus v initial cosine theta times t. And then for constant acceleration, then we have v equals a t, I guess this way, plus s initial plus v initial. And then s equals s initial plus v initial t plus 1/2 a t squared, and v final minus squared minus v initial squared equals 2a delta s. Then the parallels in projectile motion, we have vy equals v initial sine theta minus gt, y equals y initial plus v initial sine theta times t minus 1/2 g t squared, and vy squared minus v initial squared sine squared theta equals -2 g y minus y initial. So those are the special cases of constant velocity and constant acceleration. We have Cartesian. And Cartesian is the normal xy. This is inertial, so this frame does not move. Then we had polar or cylindrical. This rotates with the particle. So let's say you have something that's rotating. You can say this is u theta. Sorry, this is ur. This is u theta. So this rotates with the particle. And then finally, normal tangential, which is attached to the particle. And we only use it as a last resort. You have the particle, you have it going like this, and so tangential, t goes in that direction, and then un goes into center of curvature. So then if you had the particle down here, ut would still go in that direction, but then un would go into the center of curvature, which is this way. So normal tangential coordinate frames are annoying and not very useful in most applications, so we use them as a last resort. So equations for these: position velocity, and acceleration. All right, well, position for Cartesian, r equals x in the I plus y in the j plus z in the k. Velocity is just the derivative. R dot equals x dot I plus y dot j plus z dot k. Since this is an inertial frame, I hat, j hat, and k hat don't change. So we don't do their derivatives because their derivative is 0. And finally, for acceleration, our double dot, take time derivative again, x double dot I plus y double dot j plus z double dot k. Then polar and cylindrical, we have r equals r in the UR direction plus z in the k hat. If it's cylindrical, we include the z. Then for velocity, r dot, since this system rotates with a particle, we have to use product rule and take derivative of r and UR. So this equals r dot UR plus r theta dot U theta plus z dot in the k. And then acceleration, r double dot equals r double dot minus r theta dot squared UR plus 2 r dot theta dot plus r theta double dot U theta plus z double dot in the k. And finally, for normal tangential, since this coordinate frame is attached to the particle, its position is always 0. R equals 0. So that's another reason it's confusing, because like then you don't really actually know where the particle is. But it does have a velocity, so you can't even differentiate position to get velocity. Velocity is really, we can't say that's r dot because it's not. So this one is just v. V equals v in the tangential direction. And acceleration equals v dot in the tangential plus v squared over rho in the normal, where rho equals 1 plus dy dx squared to the 3/2 over d squared y dx squared for path y equals f of x. So then we need to know, when do we use each coordinate frame? So first thing we do is check rotation. If there is no rotation, then use Cartesian. Then if there is, we have to check if the path is known. So if R is not known, use polar. Sorry, I guess this really should be is path known. So if the path is known, then you check, is R a function of theta? If yes, we use polar. And if no, use normal tangential. So this one is last resort. So pretty much if it's not rotating, use Cartesian. If it is rotating and you can at all use polar, do that. Planar kinematics is motion in a plane. With, again, no external forces. So this is two-dimensional. We know that a rigid body is a hard object with mass and shape. And then there are different types of motion. So a rigid body can have rectilinear translation. So different types of translation. There's rectilinear, which is in a straight line. Curvilinear, which maintains its same orientation. There's also rotation. This is fixed axis rotation. And if it has a combination of translation and rotation, or it's just moving in a crazy pattern, that's called general planar motion. So it can be moving like that, can also be rotating. And we abbreviate these as TR, TC, R, and G when you're trying to identify what types of motion a system has. In here, we want to know the position of an object. Let's say here's the coordinate frame. Here is a rigid body. And we have a point A with position vector RA. And then we have a point B with position vector RB. And then we want to see the relative positions. This is our B with respect to A, and then RA with respect to B would go the opposite direction. So for all of them, we'll say translation, rotation, general planar motion, they all have position RB equals RA plus RB with respect to A. That is true for all of these. Now, if it's fixed axis rotation, then usually RA is at the origin. So that's 0, and you just have RB with respect to A. Rotation being something like this would be B, this would be A. So RB with respect to A. And then for general planar motion, same thing, RB equals RA plus RB with respect to A. Now for velocity, if an object is only translating, say it's moving just like that, or it could be moving just like this, but the change, since it doesn't change orientation, then the change in position of A is the same amount that B changed position, and the velocities are the same because they're all connected. The whole thing is moving at the same speed. So this is just VB equals VA. Now for rotational, A is not moving. Only B with respect to A is moving. So here, for rotation, VB equals VB with respect to A, which equals omega cross RB with respect to A. This omega is always in the k-hat direction. So it's always coming out of the page if the rest of the motion is xy. And then finally, general planar motion combines these. So VB equals VA plus omega cross RB with respect to A. And because a rigid body can have multiple points on it, you kind of get a chain reaction here. So if you had VC, then you would get something like point C. So VC equals VA plus VB with respect to A plus VC with respect to B, so on, for multiple points on the rigid body. And finally, acceleration. Again, since for translation, A and B move at the same speed, and they also have the same acceleration. So AB equals AA. Now for rotation, we differentiate that velocity. So omega could be changing and RB with respect to A could be changing. So acceleration of B equals acceleration of B with respect to A equals alpha cross R B with respect to A, because alpha is omega dot, plus omega cross R B with respect to A. We're differentiating the R part. And then again, general planar motion combines these. So AB equals AA plus alpha cross RB with respect to A plus omega cross RB with respect to A. And then again, this omega cross is actually B with respect to A. So if you figured it out to get velocity, then you don't have to recalculate. You can just throw that in there.